Hey folks, we're going to start talking about how we can compare groups of data. So this particular slide is kind of an overview of how we do that, and there are going to be a couple other lectures. So these sets of lectures will be a little bit smaller than the previous ones, but they'll be focused on specific sets of tests, right? So for this one, we're going to be covering z-test, t-test, and their nonparametric analogs at kind of a high level. We're setting out to answer the general question of how we can go about comparing two different sets of data. There are three sets of lectures that I'm going to put together and that you will get to go through that talk about the specifics of comparing different groups of data. For this particular lecture, we're going to focus on some general concepts about t-tests, z-tests, and their nonparametric analogs. And throughout all of these lectures, we're going to answer the general questions of, well, what do these tests do? When would you use these different tests? And what do you do when you can't use a particular test, like the t-test, where the assumptions that the t-test needs in order for it to be valid aren't met by your data? So we'll cover general concepts in this video. We'll cover comparing one sample of data to a population in another video. And then the last set of videos will be looking at when we have two samples of data and we want to compare those samples to one another. So again, we're going to talk about t-tests a lot, but we're also going to talk about the z-test and some of the non-parametric analogs. And you'll hear me use that word non-parametric a lot. I'm not going to say too much about what the differences between non-parametric and parametric tests are, but I'm going to try to give you some examples, and hopefully that will help you to really kind of understand what they mean. But if you have any questions, as always, I encourage you to reach out to me. Please don't wait. The moment something is unclear, I'd like for you to reach out so we can get it cleared. Now, I'll just spend some time here to give you just a little bit of that example of parametric versus non-parametric. The t-tests, we talk about data coming from a particular distribution, the normal distribution. Same thing with the z-test. When you're looking at other statistics, many of them come from certain distributions, and those distributions have certain parameters. And by parameters here, parameters are kind of they're the equivalent of statistics like the mean and the median and the mode, or the standard deviation and variance. But instead of calculating those for a sample, we're talking about those for the entire population. So when you calculate one of those things for an entire population, we call it a parameter. A parameter is a descriptor of a population of data, whereas a statistic is a descriptor of a sample. So why does any of this matter? Well, if you're going to use a parametric test, we assume that your data meet some of the assumptions of that parametric distribution. They have some of the same parameters or similar parameters. We know something about the shape of the distribution, and it's important for those tests because the logic of those tests really relies on that. Non-parametric tests don't care so much about the shape of the distribution. There are some things that those non-parametric tests need to be true in order for their test to be valid, but they're generally far less restrictive than parametric tests. So t-test, z-test, and their non-parametric equivalents are generally trying to answer the same question. Do these two sets of data come from the same population? Remember that population is this larger group of data that contains all of the individuals who are of interest. And the sample is the subset of those individuals of interest that we can actually get a hold of. Typically, populations are way too big, and so we don't usually work with populations. We often work with samples. But sometimes we will work with a theoretical population, right? If I say something like, I talk faster than the average person, well, I don't know who the average person is. I don't know how fast everyone talks, and I definitely did not collect enough data on everyone's speech rates for me to really say that I know what the average person speaks like. But sometimes it's useful to compare to some theoretical population. And so we may conjure up in some of these examples some parameters for those populations. Other times, what we're really dealing with are really reliable statistics, pretty consistent statistics for very large samples. At any rate, we're asking the question of, in the case of a one sample test, whether or not a sample was derived from the population we're comparing it to. Or if we're dealing with the two sample tests, we're asking whether or not these two samples came from different populations or if they came from the same population. I'm going to use t-test as an example here, but conceptually, the idea is the same when we're thinking about some of the non-parametric equivalents, and it's pretty much exactly the same when we're thinking about a z-test. What a t-test does is it tries to determine if data come from the same population by seeing how far apart the means of those groups are. And so we look at the distance between those means, and we divide that by something called the standard error. Now, standard error is standard deviation divided by the square root of the sample size. And it turns out that the standard deviation is a biased estimate of the population standard deviation. But one way to make it a little bit better, a little bit closer to the population standard deviation, is if we divide it by the square root of n. So if we sort of weight that standard deviation by the number of values that went into it, we come out with a less biased estimate of the population standard deviation. And so that's what we use because we really want to reference this in terms of population standard deviations, right? How far apart are these means relative to the standard deviation of their respective populations. And so we look at that distance between means, and we're asking how many standard deviations away, or standard errors away, those means are from one another. If they're far enough, then we get a t-statistic that is high, or rather far from zero, because we can have negative t-statistics, right? So we can get a t-statistic that has a high absolute value, and that tells us that these populations these data are likely to have come from separate populations. They're too far away from one another for us to be confident that they come from the same population. This kind of makes sense if you think back to that the neat little rule that we had before, right? That little 66, 95, 99.7 rule. Sorry, 65. So at any rate, the rule stated that you can find almost 100% of the values in a population within 3 standard deviations of the mean, right? And within 2 standard deviations of the mean, you can find 95% of the values that are in that population. And so if you think about that, looking at the number of standard deviations away from one another, that samples are from a population or that 2 samples are from one another, it makes a lot of sense as a measure for how likely those values are to have come from the same population. So the t-test is our focal test for this lecture. So when do we use it? T-tests are used when we are trying to compare 2 groups. In fact, the z-test is also used when we're trying to compare 2 groups. Or if we're trying to compare 2 groups, we can also use some non-parametric alternative. What differs between a z-test, a t-test, and their non-parametric alternatives is how we make the comparison between groups. For the z-test, you saw that we are comparing a sample to a population and looking at how far away those are based on the population's standard error. And for a t-test, you're comparing the distance between the means of each sample relative to the combined standard error for those samples. When we deal with non-parametric alternatives, we're not always comparing means. We're going to deal with the one sample Wilcoxon signed rank test in the next lecture. And for that, we're actually comparing the median of our reference group to the values in our sample. For the t-test, there are some general assumptions that we need to have met. The data need to be normally distributed. What those data are, again, depends on the test, whether we're talking about a comparison sample or both samples, or if we're talking about the population from which we think the data come. Generally, we want to make sure that we have enough data. The larger the sample, the more likely that our data will effectively be normally distributed, thanks to the central limits theorem. And then we want to know something about the variation of that sample. Different t-tests and different other comparison tests for two groups have different assumptions. And sometimes your data will not meet those assumptions. One of the nice things about the t-test is that it's relatively robust to violations of some of those assumptions. Meaning, if for instance your data don't come from a completely normal distribution, the t-test can still be valid. You really have to really deviate from normal distributions before the t-test stops being useful here. But when your data do violate those assumptions so much that the test is no longer valid, you have two options. You can either try to fix your data or you can fix the test. And when I say fix the data, I mean that sometimes it may just help to gather more data. As I mentioned before, the more data you have due to that central limit theorem, things like normality tend to become less important, right? Sometimes you may need to do something to the values themselves, like transform them. We'll deal with tests later that require your samples to have equal variances or close to equal variances. And sometimes when you have samples that don't have equal variances, we can do things like compare the square roots of those values, or we can compare the logs of those values. And when we do something like that, what it does to the variances, for smaller variances, it doesn't really move them much. But for large variances, it really compresses them a lot. And so by applying that same transformation to all of your data, you effectively force the variation to be similar between groups. But if none of that works, or if for some reason you don't want to go through a transformation or cannot, because of the nature of your test, another thing that you can do is just change the test that you use. There are lots of different tests that can handle some assumptions that the student's t-test, which is the formal name for the t-test. There are a lot of tests that can handle data that the student's t-test can't. There's a Welch's t-test, there's the Mann-Whitney U-test, which is used for comparisons of samples, and then there's the Wilcoxon rank sum test or the Wilcoxon signed rank test, which we're going to deal with now.